Okay, so we've got a group acting on a set. We've got the group that, and we've got a set X. This is a group, this is a set. And we're setting up a map from G cross X to X, and we write it Gx, and that's a member of the set X. And we've got two rules. We've got set X. We've got two rules. First of all, the identity composed with X equals X for all X. And we've also got that G1, G2 of X equals G1, G2 of X, which we require to make the group operation make sense. Okay, so it's a bit dry as we say it, but I need just a little bit more terminology before I can give you some examples that'll make it all make sense. Suppose S is a subset of X. Then S is stable under G if the following holds. If little g is a member of the group and X is in S, then Gx is also in S. So basically what we're saying is that the group action maps S to itself. Okay, and if this is the case, then we can see that the subset S under the group action, here's the whole set of X here, the group action just maps S to itself, so all these little arrows just map S to itself like that. So it's what you call stable, because S as a whole doesn't change under the group action. Okay, so I'm also going to define an equivalence relationship. Define an equivalence relationship. The equivalence relation. This term is defined in one of the screencasts in the nomenclature series, so you can look that up if you're unsure about it. And we write X and Y are in the ground set X, and then we say that X is related to Y. Sometimes you say X twiddles Y. If the following relationship holds: if Y equals Gx for some G in big G. So why is this an equivalence relationship? Well, for an equivalence relationship we need three things. We need X twiddles X, or X is related to X depending on what notation you use. We need X twiddles Y implies Y twiddles X, and we also need transitivity. X twiddles Y, Y twiddles Z. It has to imply that X twiddles Z. This one's obvious because X equals EX for all X in the group. What about this one? Well, if X twiddles Y, see how I'm approaching this? All I'm doing is taking the relationship and I'm just writing down what that means. That means that, which way around have I drawn it? Y equals Gx. Okay, that should be, oops, that should be a Y. I'll write that out again. Y equals Gx. And if that's the case, then it should be pretty obvious that G minus 1 acting on Y equals X. How do we prove that? Well, we just take this relationship here, Y equals Gx, and we observe that because both sides are elements of X, then we can just compose it with G minus 1, just because we feel like it. G minus 1, Y equals G minus 1, Gx. And this is where that nice relationship that was the second axiom of group actions crops up, which is of course equal to EX, which is of course equal to X. So the upshot of all this is that if X twiddles Y, then Y twiddles X, because this relationship holds here. So X equals G minus 1Y. What about this one? If X twiddles Y and Y twiddles Z, let's have a look at that. X twiddles Y, Y twiddles Z. What that means is that, what does that mean? That means that Y equals gx, and that also means that z equals g1x, call it g2y. So I'll just write it in, equals g2, and then y we know is g1x, so z equals g2, g1x. And so we've got transitivity as well. So this group action defines a equivalence relation. On X. So here's X, the set X, and we've got equivalence relations. There we go, and it's cutting up X into lots of equivalence relations, and the relationship is that X is related to Y if they're both in the same subset. So this X here is related to that Y there. This Z here is related to that T, and so on. But this X is not related to this T here. Now I've used T dash here because they're in different equivalence classes. Well, the equivalence classes themselves are called orbits. Okay, they're called orbits, or sometimes you call them G orbits, but they are or orbits under the action, I guess. The G orbits are the partitions or the equivalence relations or the equivalence sets of your set X. And the set of orbits is written conventionally. You see different notations for it. G backslash X. You also need the group action actually to talk about that, and this notation doesn't specify the group action. And of course you might get different orbits or different equivalence relation if you have a different group action. Even though you keep the group the same and the set the same, you might have two different, or more than two different group actions which satisfy the group axioms. And this notation doesn't make it clear which particular group action you've chosen. Okay, I'm going to stop there.